Hey everybody. So in this video, I want to talk a lot about two things, specifically heuristics as well as fractals. And so when it comes to heuristics, heuristics are a part of our everyday lives as humans. Pretty much everything, or not everything, but I mean, our every single day processes, lots of our every single day processes are dictated and governed by heuristics. The way that we see the world is governed by heuristics. The way that we do complex mathematics in our head is often dealt with via heuristics, etc. And then our brains are very attuned to heuristics. Like we want the heuristic answer. And then so when it comes to mathematics specifically, oftentimes we will default to heuristics, but oftentimes when it comes to mathematics, these heuristics rules are heuristics for a reason and not actual like 100% solid rules, right? And then so diving into that very specifically, I want to focus this video on fractals overall because like a lot of the insights that we work on very specifically and a lot of stuff that I cover on my video is uncovered first and foremost by diving into fractals and fractal dynamics and understanding kind of how fractals work better. I think a lot of people have a lot of misconceptions around fractals and algorithms that involve fractals, etc. And I think the very best place to start with that is like just a very simple visualization of the Mandelbrot set. And then so that's exactly what we're doing here. And then so the Mandelbrot set is essentially this mathematical equation here, right? So z to the nth dimension plus 1 equals 2 over n plus c. And then as long as c is under 2, then good things it will be very fluid, and then if it's over c, then over 2, then it gets weird. And then that's also the same thing for negative numbers too, what we call like not real numbers, right? Which is interesting within this as well. So I'll dive into all of them and a whole lot more within this. By the end of this, I'm going to showcase and show you essentially a image compression utilizing fractal dynamics that's like 98% image compression, not 100% lossless, but it's lossless as far as the human eye is concerned. And then you will, it will blow your socks off, right? But so diving into this, like first of all, just looking into the Mandelbrot set very specifically. So zooming in, like this is the Mandelbrot set, right? I'm going to zoom like super far into this. And then so when you're dealing with like between 0 and 2, it's this straight line basically, right? And then so between 0 and 2, and then at 2 there's a boundary that occurs, this big blob, and then this is the boundary zone, we'll call it. So then like we'll go from 0, and then this is like between like 2 and very narrow, between like 2 and like 2.1 essentially is the boundary zone. And then anything past 2 is here. And then we get these patterns. But if we zoom in on these patterns, like these kind of like outer patterns here, which we'll do here, like here, right? These are self-similar patterns. So meaning that if we zoom in and then we zoom in again and again and again, it's going to be a self-replicating pattern. Kind of zoom out here, right? And then zoom back in over here. So these are different zoom levels of these patterns, right? And then we can see from the different zoom levels how it's self-replicating patterns within this. So if this were a vector image, every single time that we zoomed in, like we could zoom in like layers and layers and layers and layers, right? And it would just be a whole bunch of different zooms. But you can see here, so from like -2 to essentially 2, we get again like the straight line zone, and then once we get to 2, we get to the boundary zone, and then past 2, anything past 2 escapes the boundary, right? It's kind of what is going on there mathematically, and then so. Let's dive into this next, which is essentially like the Mandelbrot set along the real axis and the orbits. And this ties a lot into Ash Kelly's work with regards towards like Riemannian zeros and things like that, which is why I bring all of this up, right? I can't, it all starts to me and overall with fractal dynamics, and then from fractal dynamics, it's like harmonics and resonance, etc. But it all ties together as a unique unit with kind of, to me, fractal dynamics as the core that ties all of that together, right? And then so this is pretty cool because this is looking at the Mandelbrot set, it just so in different visualizations, right? And then so this is like what it looks like in that boundary zone, that unique zone that we were looking at here between like essentially like we'll call it like -1 to 1 is that straight line, and then past that you start getting like kind of weirdness, and then it's just it explodes further and further, right? But what's interesting within this is that it happens both ways. So it happens at -2 and +2. So if I go back, maybe I hit the wrong button here. There we go. Let me close out of this. 1 second. There. And then let me find a different image of it here. Maybe I won't. Let me go back up. Cool. So I guess this is what I'm gonna find of it. So it's this way at like this way at -2, and then this way at +2, right? So then it's how most people think about this is that like this is imaginary and then this is real. Like imaginary because you're in negative territory, and then this is what happens when it goes to again like -2 and above. But it still gets that infinite explosion, but it's just kind of weird, as opposed to this in like real world terms when it gets to +2, and then so you get essentially like 3 different states and 3 different phases of this algorithm, right? This is all like the same exact algorithm, that same exact equation that we're running at, right? But if you're just looking at it in a narrow band, you're only going to see this, like, right? And if you only focus on this, or if you look at it only in a big area, you're only going to see this, or in a negative and like an imaginary numbers, you're only going to see this. And then so this is very like this kind of like defies a lot of stuff that we think about overall when it comes to fractals, how they work, fractal dynamics, etc. Right? And then so to me, like I've been like over a year now exploring very deeply into like fractal dynamics, right? And then so this notebook here is like understanding fractal dimensions. This is something that I made last year, and then I'm just exploring fractal dimensions at different dimensionalities, right? So to me, I started noticing a difference between fractal dimensions, specifically between like this fractal dimension of 2.5 and then lower, and then I'll show you the bottom ones. I think more we get start going into here, right? So in this instance. In this first instance, I'm measuring kind of agents and agent dispersion within fractal dimensions, and then in this first one, I'm doing it at fractal dimension like 1.10, and then so I'm just going to scroll through, and then you're going to see the dispersion patterns just over time series, right? So over time of agent distribution, which should be like. There should be a patterns that emerge from this, but we'll take a look at it in fractal dimension 1.10, right? And then so and we're just going over different dimensions, and dimension 1.5, dimension 2, and then so from I just gonna go back up here, right? So like. To me, there's no discernible pattern within this. This is like chaos, right? Like, it doesn't make sense. Like, I don't understand why the dispersion rates are the way that they are in this instance when we go to like up to 2, right? This is everything that like this kind of defies everything that I know about what should happen within this. What I think should happen within this is like let's take a look at fractal dimension 2.5, right? So we have time step 40, time step 120, time step 160. And then so what happens, right, is that the agents want to start clustering towards the edges, so they want to cluster towards 0 and 100 in this instance, right? They want to move away from the center over time dimensions. And then so we see here time dimension 0, we have like almost even dispersion, right? And then we see they're moving away from the center, away from like a movement away from the center towards the edges, right? More movement towards the edges, and then that's exactly what we see within this, whereas up here, I'll go back up here, right? It just, I mean, just random, like more randomness than movement towards the like direct movement towards the edges at every single time step here, right? Like here's time step 80, 120, it changes, but then at 160 it's back to this. So it's, I mean, like it's just a major difference there in dimensionalities. And then so this is like entropy over time at these different dimensions. And then what you'll notice, like they'll look the same, but the like scale of these graphs are vastly different. But then this is where we'll start to notice kind of like major fluctuations and differences. So like if I look at, temperature here, I can see entropy going up like over different time steps at exactly 2.5 fractal dimensions. Just start measuring, things like here. Very specifically, and like the reason why I highlight this type of notebook is I start noticing things like this here, right? Where this is like comparison of peak like wave amplitude across geometries, and then so Euclidean, hyperbolic, spherical, and fractal geometries. And then very specifically, what I notice and what I can see here is like patterns that emerge like this within fractal and hyperbolic geometries, which kind of in my mind made me think of this. Like that's kind of what is occurring here. If you were to visualize out to me, it's like this same type of effect going on there, right? Where like you have, if you measure in this range, so in this time step, like between time step, we'll call it like 120 and 140, 130, you're going to get vastly different readings than if you measure any other time step. And that's just because it's like something is going on unique there, right? And it's very unique at that particular time step. And then you can see kind of that same sort of breakage here. The fractal geometry is the red one, right? So it's the only one that has that bending in it, and that bend is like stuff like this, like weird things happening within it, right? And then so going down further, like this is just looking at like wave function evolution as in different geometries. And then this is entropy, and it's so very specifically at different time steps across the different geometries. And we see major, like just goes off a cliff, like right at 2.5 fractal dimensions, right? Which is why I start getting focused very specifically on that. And then you can see here that it's kind of the door to me, 2.4 compared to 2.5 fractal dimensions. Weird things start happening. Physics starts changing right at that ratio, right? And then we can see entropy over time changes based off of fractal geometries. So I realize at this point there's a correlation between fractal geometries, entropy, and a lot of different aspects and characteristics, right? And then so what can I do with that in real world terms? I know I told you I'd show you something cool that comes out of this. And then so bottom line, like taking all of this math together and then like understanding this, this was like one of my very first experiments within this, right? And then so this is like a Sierpinski triangle image compression. And then so this is utilizing Sierpinski fractals. And then in this instance, what I'm able to do, essentially I project the images into like fractals. So this is the original image and then the reconstructed image, right? And the reconstructed image is 100% based off of a fractal. And then so we can see here, original size compared to compressed size, not very good here. But it's a little bit of compression, right? We get some compression compared to the original, and it looks to me very good, right? And then it's just like free compression essentially, just by compressing it very simply into like into a fractalized terms. But then I wanted to get like deeper, right? And then so this is what I start playing around with it. This is what I want, right? So essentially, if you can pull this off, like, and it looks right, like so here's the image, and then so what I do in this instant, like I'm trying to visualize this for you in simple terms. Let's take a look and go back here, right? So I'm essentially like trying to save the image in like one of these, like one of these outer like fractal edges, right? And then like I'm just like okay, like take the whole image, and then let's say that the whole image would be this whole entire block, right? Like everything here, and then like and this whole sheet, like this whole white sheet. But rather than save the image in the whole white sheet, I want to just zoom in, and then I just want to save it in like a little one of those fractal areas. And if I can save it in one of those fractal areas, how this fractal works is it's self-replicating, right? So if I could just zoom in enough, I could save it into just one of those, just stamp it into like a little one, and it's gonna stamp itself and then kind of go out from there, right? And that's what I'm trying to do here. And then so that's what I do. And then like I can't get the stamping, like, see, it's not like one, like I need to like I need to dial it just like a little bit better, right? Like my stamp is it's fractalizing too much. Like I'm not getting it 100% in the center of the fractal, right? Like I just like I need that exact center of the fractal, and if I could get it in that exact center, it's gonna get me this, and I'm super close with this, right? Like it's just like, man, it's just like a little bit off, but this is like the amount of compression that is going on here is crazy, right? So if you could dial it and fix it, you'd be set. But I can't get past that. Like, but you can see like the compressed size is crazy of this, right? Like, so like of this, like if I can fix this, and I'm sure I could fix this, like give me money, I could fix this, right? But so if you go here, like the original size is this, and then I get it down to this. So several magnitudes, right? But I mean, reconstruction loss is crazy because it's this, right? So, and I could dial it. There's a way to dial it, like, but so this proves out that it's possible, right? And then here I gave up, and then I haven't touched this since, but like at this point, I started getting deeper into other projects overall, but like as far as like compression, like this is actually like an avenue of compression. I don't think I've shown this on my channel actually, but like I would recommend this type of compression over anything else, like this fractalized compression, right? And then so I just again highlighting and why am I talking about this overall? It just I think it's important. Like a lot of people again utilize heuristics and very simplistic examples that they think are like mathematical proofs when regards towards a lot of things, when a lot of things aren't like 100% mathematical proofs for a reason, right? They're theorems for a reason because they haven't been 100% proven out, because we have to prove out and account for situations like this, which happen more than you would think, because this is tied very specifically to chaos theory. And when it comes to AI overall, and I didn't do it, but it all comes down to chaos theory, right? So there it is, and how this all ties together. And then I'll leave a link to a few of these notebooks here. I'll leave a link to the Exploring the Mandelbrot Set, as well as this one here, so you can take a look and play around with these. And if you like this type of content, please like and subscribe. Thank you very much.